So looking at this system, we want to look at some algebraic methods for solving this linear system. And we're just going to, once again, reach back into elementary algebra and think about the things that we can do. In particular, one thing I can do is I can notice that the y and the minus y in the first equation and the plus 2y in the second equation have opposite signs. So one thing we might do is take the first equation and multiply it by 2 so that we can add it to the second equation and cancel out the y's. So I'll multiply the first equation by 2. Oops, that's not going to be equal sign. We're going to multiply the first equation by 2 to get the equation 2x minus 2y equals 2. And then we'll add that to the second equation, which is 3x plus 2y is equal to 8. So I'm going to multiply the first equation by 2, and then I'm going to add the two equations together. These are all legal moves in solving systems of equations. So I'll add the two equations together, and I'll get this new equation. 5x plus 0y is equal to 10. So we've reduced the number of variables to just one. We went from 2 equations with 2 unknowns to 1 equation with 1 unknown. And then this tells us that x is equal to 2, which is half of our solution. So what we did was we multiplied the first equation by 2 and added it to the second equation to cancel out the y's. So this looks like 5x plus 0y. I want to think of this plus 0y. And then we could simplify that to look at 1x equals 2. Then I could take this and I can go back and plug in to find y. Any questions? We can also multiply the second equation by a -3, and then that would cancel out the x's. So maybe we want to do that. Let's take a look what that would look like. So I could take the second equation, multiply by -3. Oops, not the second equation. This is what happens when I don't train in the off season. It's like spring training in baseball. So I'll take the first equation, x minus y equals 1. I'll multiply it by -3. So it becomes -3x plus 3y equals -3. Now when I add the two equations together, the x terms cancel out, and I end up with 5y is equal to 5. And then that tells us that y is equal to 1. And so there's our solution. So more importantly, we have -3 plus x plus 3x gave us a 0x. And so then we divide by the 5 to get 1y is equal to 1. So what we notice that we can do is that we can multiply one equation by a constant and not change any of the solutions. And if two equations are both to be true, any sum of those equations will also be true at the same points. That sentence didn't come out the way I wanted it to. So if I multiply an equation by a constant, a non-zero constant, I get an equation with the same solution set. If I add some equations together, I get an equation with the same solution set. I don't change the solution set. We can multiply by a non-zero constant. We can multiply by a non-zero constant. We can add equations together. and neither of these things change the solution set. We can multiply by a non-zero constant, we can add equations together, and this will not change the solution set. So does everybody remember our elementary algebra from long, long ago in the before times? All right, so what we want to do is we want to take this system and this method where we're just kind of figuring out what to multiply by, and we want to codify it into some system that we can always apply. We want to codify this into a nice system where we're going to do the same thing every single time. So what we can do is keep our organization. We want to be organized so we have to write less. We want to write this just the number parts. If we can decide that we're going to be organized about things, we can just write down what the numbers are. We can look at this equation, this system, x minus y equals 1, and 3x plus 2y equals 8. We can take this linear system and encode all the important information into a matrix. So I'm going to write this as the first column is going to represent the coefficients of x, 1, 3. The second column will represent the coefficients of y, -1, 2. And then the third column will represent the constants, 1, 8. So this is what was going to be called an augmented matrix of the linear system. So this is an augmented matrix. So here's an augmented matrix of the linear system. Any questions where it came from? Just pull out the coefficients, write less. And it's organized into columns. This first column is the coefficients of x, this second column is the coefficient of y, and this third column is the constants. I'll use a k, I'll use the mortal constant for the constants. Sometimes in an augmented matrix, we draw a vertical line or a dashed line to remind ourselves that we're dealing with an augmented matrix and not just some other 2x3 matrix. So sometimes we use a vertical line to denote an augmented matrix. Sometimes we use a dashed vertical line to denote an augmented matrix. Now, the operations that we performed on the equations, multiplying an equation by 2, is now going to be an operation that we perform on a row. And then adding the equations together, that's another operation we performed on the equations. That's going to be an operation that we perform on the rows. So equation operations, these equation operations up here, multiplying by a non-zero constant and adding equations together, are going to become row operations in the augmented matrix. So these operations, equation operations in the linear system, become row operations in the augmented matrix. Equation operations in the linear system are row operations on the augmented matrix. Equation operations on the linear system are going to become row operations on the augmented matrix because each row corresponds to an equation. Each equation will correspond to a row. So that's the main thing. So now all we have to do is take these operations and apply them to an augmented matrix to get ourselves down to a solution. Any questions before we go on? How's everybody, okay? All right. So let's take a look at this augmented matrix and the linear system. So I'm just going to get my linear system and my augmented matrix up here. So my linear system says x minus y equals 1 and 3x plus 2y is equal to 8. And this corresponds to the augmented matrix 1, 3. I'm reading it by columns. 1, 3, negative 1, 2, 1, 8. So what I'm going to do is I'm going to multiply this first equation by negative 3, and I'm going to cancel out the x's. So if you recall, that was one of the operations that we performed. I'm going to multiply this equation by negative 3, and I'm going to add that to the second equation. So I'm going to do the same thing over here. I need to see, and it's going to be my new second equation. So I need some notation for this, because it's math class, and we need notation for things. So I'm going to multiply the first equation. I'm going to multiply the first row by negative 3, and I'm going to add it to row 2. So I'm going to take negative 3 times the first row and add it to the second row. So negative 3 times this first row, it gave us negative 3x plus 3y is equal to negative 3. And I'm going to add that to the second equation, and then over here, I'm going to add that to the second row. Notationally, I write them a little bit above. So that negative 3 times R1 is going to be the row negative 3, 3, negative 3. I'm going to add those to the second equation, or the second row. And that's going to give me negative 3x and 3x is 0x. 3y plus 2y is 5y. Negative 3 plus 8 is equal to 5. My first equation is still the first equation. X minus y equals 1. So in my augmented matrix, my first row stays the same, 1, negative 1, 1. But my second row now looks like 0, 5, 5. So that 5y equals 5, back in elementary algebra, when we knew all we had to get was a y, then we can go back and plug that in to find the x. That's where we stopped with these operations. We knew that y was equal to 1 at this point, so we were kind of done. We didn't care. But now what we want to do is try to build a system where this will move forward, where we can move forward and take care of more equations as we go along. So what we did next was we multiplied this equation by 1/5, or we divided both sides of this equation by 5. So I'm going to replace this second row, 0, 5, 5. I'm going to multiply 1/5 times row 2, and that'll be my new row 2. In the same way that here, we multiplied this equation. In the system, we multiplied the second equation by 1/5 to find out that y is equal to 1. And that told us. And then still, x minus y is equal to 1. So we still had the information, x minus y is equal to 1, but now we found out that y is equal to 1. As a row operation, we can do the same thing. We have by columns 1, 0, negative 1, 1, 1, 1. And this second row, 0, 1, 1, corresponds to the equation 0x plus 1y equals 1, which tells us that y is equal to 1. Next, what we can do is we can use the fact that y is equal to 1 to solve for the x. Before we do that, the way we want to think about these row operations is we want to look at this 1. I want to think about getting a 1 here and using that 1 to get zeros in the rest of the column. That's the words that I'm going to use to describe this row operation. Use this 1 to get zeros. This is going to be called a pivot. A pivot's going to be a 1. It doesn't have to be a 1, but for reduced or echelon form, we're going to want a 1. And we're going to use the 1 to get zeros in the rest of the column. Use the 1 to zero out the column, the rest of the column. So we're going to identify this 1 in the first row, first column as a pivot position. That's where we use that 1 to zero out the rest of the column. Any questions? All right. So what we're going to do now is we're going to perform another row operation. So now this column is what I consider done. There's a 1 and 0, and the rest of it's zeros. So I move on to the next column, and I'm going to go over one column and drop down, and here's my next pivot. This is the next pivot. In that pivot position, I'm going to use this 1 to get zeros in the rest of the column. So I'm going to take row 2 and just add it to row 1, and that's going to be my new row 1. So my second row is going to stay at 0, 1, 1. And I'm just going to add 0 plus 1 is 1. 1 minus 1 is 0. That's why this worked. And then the 1 plus 1 is 2. And now this column is done. Now, if we look at the system that corresponds to this augmented matrix, that first row, 1, 0, 2, says 1x plus 0y is equal to 2. And the second row, 0, 1, 1, says 0x plus 1y is equal to 1. Any questions? This last augmented matrix is called the reduced row echelon form of the matrix. The reduced row echelon form of the matrix, which in this case is the augmented matrix of a linear system. Questions? How's everybody, okay? Cool. I'm going to stop recording.